Welcome folks, and in today's video we will talk about Hooke's law, and I'm going to use and introduce a character called Bob to discuss this. And spring is here, and Bob decides that they want to go for a wee walk before realizing that it is spring, so an umbrella is going to be required. There, that's better. Also, Bob's going to have to reach for his glasses, his spectacles, so that he can see what's in front of him for this walk. So everything's going according to plan for Bob. And then finally, Bob gets a little bit of an idea, starts walking outside and realizes, oops, I forgot to lock the door. So in this tale of Bob going for a walk in the springtime, there is something which is joining together all of these things, and joining together that's this story, and that is the concept of springs. And that's what we're going to talk about today, and this is something which we will discuss Hooke's law with, because umbrellas, spectacles, locks, microwave doors, any door in fact, all work on the principles of spring energy. So let's have a look at some elastics. And springs are really just a form of an elastic object, which means that it will return to its shape when stretched or compressed. And hopefully you can see in the top left, there's two examples of springs. There is the brown spring and the green spring. And not all springs are created equal, and hopefully we have been around springs enough to realize that it would be much harder to stretch one of the springs than the other. And I'll leave you think about which one would be harder to stretch. So we have a scenario where we have the spring which is on the left, this here, and then we have the spring in the middle and the spring on the right. And just to introduce some terminology for these things, when the spring is pushed in, a force is used to push it in, we say that we are compressing the spring, and that's compression. And then the one on the right, of course, that's extended, and we can also say that the string is stretched. And the one on the left is in its natural position, and there's a phrase for that. We say that the spring is in its natural normal position, and so it is in equilibrium. Now, the amount that the string is stretched, we have a terminology, we have a term for that, and we call that the extension of the spring. So the actual distance that the string has been extended or stretched, we call that the extension, and that is in meters. And it turns out that if we have a spring and we extend the spring and we apply a force to it, that this is a very predictable relationship between force and extension of the spring. So if we have on the left, we have a 100-gram weight and we apply that to the end of a spring, and we take the same spring and we apply a 200-gram weight, and then we measure the difference in extension point, we will see that it's extended twice the extension. So there's a relationship between the mass applied, the force applied, and the extension of the spring. Now, of course, we represent F with the force as F, and we represent this extension as delta X. And you'll sometimes see it as delta L also. So F is proportional to delta X. Another way of writing that, we can change that to an equation by putting in a constant value. And this constant value here, this K value here, is important because this is a measure of the stiffness of the spring. And different springs have different amounts of stiffness. And this value here is called the K constant. And it is a value that's measured in newtons per meter. So if we were to actually have a look at this, and we were to graph, do a lab, and we were to graph for different amounts of forces. Whoops, that's a jagged line there. And we were to graph that extension against the force applied. What we would expect to see is we would expect to see a proportional relationship, a linear proportional relationship. Now, there is an important thing to say here. When you stretch a spring a certain amount, after a certain point, it stops behaving like an ideal spring. And this point here is called the elastic limit. And if you've ever worked with an elastic band and you've stretched it, you'll realize that there's a kind of a point of no return for that elastic band where it won't return to its original shape. And therefore, it's not elastic anymore. It's now deformed or inelastic. But up until this point, so all in here, the spring has a very predictable behavior. Okay, and we're just going to use a simulator from the wonderful folk at PHET, PHET, just to show this in action. And so if I use this tool to stretch the string, what we'll see is various things happening. So we can see that it's 20 newtons and we're extending to 30. Now, each time we do that, it's going up by a very predictable amount of distance and about 0.050 meters. And if we have a look at a similar spring, and we're just going to extend and put the same amount of force on it, 40 newtons, we can see that it extends in the green by 0.2 meters or 20 centimeters, the same. Now, if we make this spring constant, we double the spring constant, what we see is that the stretch is half of the stretch. So there's an inverse relationship between spring constant and distance that it's going to go. If we increase the spring constant to 600 newtons per meter, we see that it drops even more in a linear fashion. So this spring constant, this K value, this K constant, when the K constant is big, it means that it's hard to stretch or compress. And, when the K constant is small, it would be the opposite of that. So now we'll do a typical just introduction worked example problem. How much force is needed to pull a spring with a spring constant, that's disappeared from me there, a spring constant of 20 newtons per meter, a distance of 25 centimeters. So a couple of things that we need to establish here. Of course, we already talked about how the force applied to the spring is matched by the backward restoring force in green that the spring is going to apply. So when we stretch it, and the more we stretch that spring, the more the force is going to be that resists it. Okay, the second thing that we should do is we should realize that the spring constant is in newtons per meter, not centimeters. So we're going to have to change the centimeter value here, and we're going to have to write it in as meter. So 0.25 meters. And the force that's needed we know the spring constant and we know the stretch now. And so we're just going to multiply the two of those together, and we're going to get 5 newtons. That means that we're going to need 5 newtons to stretch a spring that distance. So maybe you might be able to stop the video and figure out how much force would be needed to stretch the spring 25 centimeters if it was a spring constant of 60 newtons per meter. So hopefully you found this video useful as an introduction to springs and the law which governs them. They have a very predictable linear behavior, and so the stretch of a spring is tied into the force that's applied to it, and that behavior is part of what we call Hooke's law. If you enjoyed this video, please give us a wee thumbs up and hit that subscribe button.